Alright. Oh, I'm on. Brilliant. Are you ready? Hi, those who don't know me, I'm Hugh Sanderson, responsible for the Hxcpp backend. Going to talk about what's new in the backend for this year. Got a bit of a theme going here with breaking bad, but I'm hoping that there's not too many bad breaking changes going on. Originally, I thought there wasn't really that much to talk about, but I actually spent a lot of time under the hood in the back end. So I'll just go into some of the gory details. So the highlights of the last year is a big refactor in the way the OCaml code was written. The original code was, over 5 years old now, and when I first started, I didn't really know what I was on about that much, so I've learned a bit since then. I've also upgraded some of the internal structures in the actual header files that Hxcpp uses. The enum interfaces and anonymous structures have all had a bit of an overhaul, and again, some of those date back 5 years or more, so it's probably a bit due. I've done some GC optimizations. Actually, these were already released in 3.2.201 or something like that. So you may have already seen these optimizations in your own code. They were mainly to do with some micro optimizations, which just involves real code level tiny changes. Defragging, which is an optional thing you can use to stop holes in the memory, which I'll talk about that a bit later. And just setting the default size of the available memory space was a pretty big win that only took one line of code. So as I said, I'll talk about those in a little bit. I've also made a big change with the 3.3 compiler, and Hxcpp is moving towards binary free. So I won't be distributing, or I won't be requiring the NDLL files that normally ship with Hxcpp. And to compensate for this, I've added a compiler cache to cut down the compile times. So if we have a look inside into the guts of the compiler, as I said, a substantial rewrite of the OCaml code, and most of this was about being able to reason better about what the Hxcpp compiler thinks the type is and what the CPP compiler thinks the type is, and knowing when to do a conversion and when I need a cast and when I don't. Also, the generated code output looks quite a bit different now. I'm not sure if any of you have ever delved into the generated code, but I'm hoping for a much better correspondence with your Hxcpp code. So if you wanted to use a native debugger, it would be more viable or more interesting. And I've added this annotate source define for CPP and the sepia debug if you want to get into try to get inside the mind of the Hxcpp backend. That will add some comments to the code, which may or may not mean anything to you. So we start with the simple Hxcpp code, gets compiled into CPP now. You'll notice the line numbers are on the left, more like you would see in a standard IDE. There's not a lot of temporary variables hanging around, which I actually can't take credit for that because that's come from the core compiler. You see the for loop's changed to a while loop, but otherwise there's a pretty good correspondence between what I wrote in Hxcpp and what we see now in CPP. The sepia code, if you compile with -debug, you actually get an ASCII file, which looks a lot like the AST dump. And now I've just got these little hash comments of println and the class name and a few other things, which just make it easier to follow if you want to get in there and see what's happening. So that's just if you want to tinker with some of the output options. So into the structures, I redesigned some of the structures to minimise the number of allocations and the amount of memory required to represent some of the more common things. I introduced the CPP variant type, which has just got a little type flag, which can be string or bool or object or something like that, and the data. And so it's slightly larger than a normal object, but it means that a single struct here can represent any of the Hx types. And it's slightly slower to actually read from the structure because you have to check the type to see if it's a string, then you need to do something, otherwise you do something else. But it's much faster to set because you don't actually need to box a type like you would with a dynamic. So you can set a variant to an integer. It's a very fast operation, and you don't need a memory allocation, which adds up quite quickly. So I think it'll be a good bonus across the board for people using some of these more dynamic access methods. And this is used when you query a type by name now, a member by name from an anonymous type. It's all using variant now instead of dynamic. So here is an enum and what it used to look like in 3.2. Here enum val, it's got 3 fields, an int, string, and object. Before, the enum object used to have an array of arguments. The array would have a set of byte data, and each of those arguments would itself be a boxing of one of those values. So you can see the simple enum here would have maybe five or 6 allocations associated with it. Now in 3.3, I built a single structure with a single allocation that has enough room at the end to stick the parameters in, and I just stick the parameters one after the other in a variant format. So it's much more efficient and compact type and doesn't require any additional allocations like it did before. Similarly for an anonymous structure here, I have you declare an anonymous structure with 3 fields. A is an int, B is a string, C is some kind of object. In 3.2, this would be represented by the anon class, which has a hash object, so hash itself becomes an allocation. It has an array, which is a bunch of bins, so that's an allocation. Each one of those bins points to a linked list of elements, each of which is an allocation. And they themselves may require boxing if the array is not homogeneous, as it isn't in this case. So in 3.3 now, for an anonymous structure where you declare it in this kind of style here, it uses a single allocation using the variant types again. So it can list the 3 members. Here I've put them out of order alphabetically just to indicate the fact that it's using a hash rather than a string order to get at the anonymous fields. But it's still a valid anonymous object. Like you can delete these fields from it and they will go away. And I've got this hash at the end here, which is the same structure as in the 3.2, and that's kind of like an overflow field. So if you start pushing additional stuff onto this, you'll basically have a similar performance to how it was before. I've also added this metadata fixed that you can add to an anonymous structure at declare time. So if you, when you actually write an expression like this, this hardwires the types into the anonymous structure, and you can use up to 5 types with this optimization. And in this case, they're not boxed. They're also not variants. They're strongly typed, sitting in the anonymous structure with some kind of, and the string lookup there is reasonably well optimized as well. So you can use, you can't put this on universally across all your Hx code, because if someone gets one of these structures and expects to be able to add a member to it, they won't be able to, and you won't be able to change the type of one of the members, and you also won't be able to delete it. So you can't use this everywhere, but I think you should know when your little anonymous structure is designed to be a kind of fixed thing and you're not really looking to add stuff to it, like maybe you want to return 2 values from one function, you could use the fixed notation to deliver them. And this, again, uses a single allocation, and it's kind of fairly optimal for an anonymous object. Interfaces is something else that I've changed the implementation of a couple of times in CPP. In 3.2, they involve creating a little delegate object, and when you So when you assign an instance to an interface type variable, it creates a little delegate that has like a trampoline function. So when you call a function on the interface, it actually jumps off and calls that function on a different object, which allows me to do, to have different objects implement the same interface. The problem with this is that it obviously requires the creation of the extra delegate, and there's two function calls involved when you make an interface function call. It's got to call the little delegate object, and then he trampolines it off to the real object. In 3.3, it still does require two function calls, but they're slightly different. Now, when I assign it, an interface is actually just typed as dynamic. So effectively, I erase all the type information when you assign it to an interface. And at call time, I query the function array from the instance. So here, in this case, I'm querying the interface out of it, that gives me an array of function pointers, and then I call a function on one of those. So instead of having the two virtual functions I did in the 3.2 case, I've got one query function followed by a member function pointer, which actually adds up to be, it's probably slightly slower than the 3.2 case, but again, it avoids the allocation, and it also avoids issues with the interface function the interface implementation object being exactly the same as the interface itself. They're physically the same pointer, whereas before they would be different pointers. So if you tried to compare them, I have to do a thing where I have to check to see if it's a delegate or not, and then compare the pointers. So as far as your own code goes, you might not see much difference there, but it has simplified some of the code I've got, particularly like arrays of interfaces, which is something that was a little bit problematic before. And yeah, finally there's the array of dynamic, which has always been a bit of a pain as far as CPP goes. Hxcpp language doesn't really seem to mind too much whether converting between an array of dynamic and an array of something else, but in CPP the array of dynamic has quite a specific memory layout, and it's really just not compatible with an array of float. And so you would run some code like this where you'd assign an array of ints to the array of dynamic, which is fine. I can then push a float onto this array of ints, which is also fine because it's an array of dynamic now. Then casting it into an array of float, which is kind of simulating something maybe like in a JSON parsing scenario where the developer knows that it's an array of float because he stuck a bunch of floating point strings in to his JSON string, but now Hxcpp has made this typecast. Before in 3.2, at this stage, B would have to become a copy of A because they can't share the memory representation because they're quite different structures. But now in 3.3, the array of dynamic actually is a little wrapper and has an implementation array sitting underneath it. So at the point where I cast it to an array of float, actually it changes the underlying implementation to an array of float, which can then share with B. So in this case, A is a dynamic that's pointing to an implementation of array of float, and B is pointing to the same one, so that when I change B, A also changes. So that's just it's been on my bug list for about 4 years, so it's kind of good to get a solution for that. And I think it's actually a pretty good solution because this actually allows the array of dynamic to stay as actually an array of integers, if that's really what it was. If you only ever push integers onto this array, the underlying implementation is an array of integers, which is probably what you want, and it's more efficient than having an array of box dynamics. Just a little point down the bottom here, if what you wanted, instead of using an array of dynamic, if you're saying you're going to have an array of anonymous objects, you can use this little array emoji here, which is saying it's an array of object or something with fields, which explicitly excludes strings and integers and floats. And by doing that, it means I can use a more efficient array structure because it doesn't have to be able to polymorph over to an array of integers. And this could well be what you mean. So if you actually mean an array of objects rather than an array of dynamic, you'll get a performance improvement on CPP by writing it like this. So the gory details, the garbage collection. As I said, this code's already been out there for a little while now. It was released in the CPP Hxcpp, independent of the Hx compiler. The main change was I inlined the new operator into the header file for the most part. If it can make an allocation without really having to delve off into the internals and allocate a new block, it can just make an allocation there in line in the header file. And I also refactored some of the code that we need to do in order to keep track of the conservative marking to understand what actually is truly a GC object and what's not when I find it on the stack. So I refactored that to be, I thought I had quite a clever little way of doing it before that used no extra memory, but it turned out it was reasonably slow. So now it's not so clever, but it's much faster, and that's probably where it's going to stay. And so that was quite a nice speed improvement. On the high level, I've added this GC moving define, and that will allow for defragging, which means when you allocate a whole bunch of objects in a row and you then say every fourth object is needed and all the ones in between aren't needed, you still have a problem where Hx can't allocate an object that's going to fit in the middle of those objects. So you end up with a whole bunch of free space between the objects that you've retained. Defragging moves all the used objects down to one end of memory and all the holes up to the other end of the memory, and therefore increases the amount of contiguous memory that you can allocate into. Only problem with the GC moving and why it's not on by default is that any back end that is not expecting its memory to move on it because it's got some kind of internal pointer to it is not going to like having the memory moved on it. So it's kind of opt-in at the moment. I think we'll maybe see how it goes over the next year and maybe look to put it on by default maybe next year once we've seen how some of the native code can interact. Basically, probably explicitly pinning the memory and saying don't move this bit of memory on me while I'm using it. Yeah, also tune the default memory size. That's really just a matter of start off with 20 megs of free space instead of 2, and that means that you go 20 megs before you have to hit a GC allocation. That's pretty good. You can control that yourself, so depending on your app, you might like to fiddle some of those parameters that I think are exposed in Hx, but you can also change them with environment variables at runtime, I think. And I've added this GC big blocks define, which allows you to have more than 1 gigabyte of memory under control of Hxcpp. It just uses a slightly different structure. It could probably go on by default. I think it was a teeny weeny bit slower for a small project, but that's not always an option there. I think you'll know if you need more because it'll crash on you, and that's the time to start putting it on. So, how does this all affect you? I have a benchmark, which is the Mandelbrot image generation benchmark, which is inside the Hx compiler test directory. And contrary to what you might expect from its name, it's actually testing memory allocation speed rather than compute speed, because I've written it badly, deliberately or otherwise. It creates a bunch of complex objects with just 2 fields, I and j, plus a bunch of RGB objects, and it holds a large array of these, which actually is a bit of a problem for Hxcpp because the collect time is proportional to the amount of retained data, and this is retaining quite a lot of data. So it's quite a good or hard test for the back end. So originally in 3.2.1, when I just used anonymous objects for the RGB and the I and j, it was taking 113 seconds to run on a 25 size, if you look, there's a 25 parameter in there. And if you use strongly typed, it's 8 seconds, which is, a little structive complex with a float I, float j. So having introduced the GC improvements at the end of last year, the anonymous types kind of halved, so that was quite good for the GC backend. Now in 3.3, when I moved the anonymous structure to the variant structure, it's gone down to 18 seconds, so this is another 3-fold improvement over what it was in 3.2.1. And if you add the fixed metadata, it goes down to 11, which is like a 10x improvement on the original anonymous speed. And now 3.3 typed, it's down to 2.28 seconds, and that's due to the GC optimization. So you can see how heavily dependent on GC performance this benchmark is. It's like a 3x improvement from the improved GC. And if I turn on 64-bit compile, it gets actually under 2 seconds. So this is on a Windows box. So that's been quite good. And so, you know, you might think, well, that's fantastic. What a sensational target the CPP target is, until, yeah, JavaScript comes out 1.1 seconds. I guess it's got an awesome GC allocator, is really my conclusion. And it's effectively it has almost the same amount of information the CPP compiler has, because it's relatively simple for it to deduce the fact that you've got two floats, you're doing multiplication operations, so it doesn't have to really guess whether it's an object or a float or whatever. And so there's still some work I can do. JS has a slight advantage. It doesn't have to worry about any of the conservative marking stuff that I have in CPP, and it can be single-threaded, so it doesn't have to get a thread local context for the allocator, but it's still doing a pretty good job. But not as good as Java, which is doing even better. Gotta give the Java guys and the Java backend guys some credit here. I think it's got an awesome GC allocator. A lot of smart guys have spent a lot of time on it. So I don't think I'll ever get as good as Java on a straight memory allocation benchmark, partly because of those reasons I outlined, but also it's the sheer manpower and tweaking every last, squeeze every last bit of performance out of it. But still, I would call these all compiled targets. The JS, I'm calling a compiled target because it's got its JIT and it actually is doing something quite similar. If I look at Sepia for the same benchmark, which is an interpreted thing, 46 seconds, and Nico, 95 seconds. So this is in this graph, that's not looking quite so dire, but it's there's still some work to do. So the CPP standard libraries, STD, regex, ZIP, SQL, iSQL, and now SSL, which has been a contribution that I haven't had to do anything for, which has been great. So these are now no longer linked as precompiled libraries or NDLL. So in 3.3, you simply do not need these binaries anymore. Currently I am shipping them just so that if you've got code that expects them to be there and you try to copy the DLL, it won't error out on you. But so for a transition period, I will still ship these libraries and DLLs, or if you're using the 3.2.1 compiler, you'll still need them. But eventually they might go away. I've changed the calling from the FFI call into just a direct normal C call. Seems much easier, sort of under the why didn't you do that before kind of basket. That's been a little transition there, but that's good. The compiler is smart enough to only pull in the files that it needs, so if you don't use regex, it doesn't need to bring in the regex files. And the good thing here is that I no longer have to deal with different versions of the compilers. Like if I ship the library, Visual Studio 2013, libraries don't work with 2015, so I either got to ship both or choose one, or there's sort of really no good answer there. And so this ends up being a little bit more compile time because you actually have to compile these on your own machine if you use them. But I have a solution for that as well, and that is in the cache. The CPP compile cache, you can opt into it by setting this configuration variable for Hxcpp to use. Your Hxcpp config XML is probably the best place to set it. You point it at a directory, and then the CPP compiler will use your cache. Currently, its default size is 1 gigabyte, but you can change that. I haven't got a good feeling for what size it should be yet. Maybe more. I'd also recommend sticking it on a solid-state drive with a little bit of area there for it, just to make sure everything runs nice and fast. And you can manage it with the Hxcpp run Hxcpp. There's cache. The cache has got a few commands, list and clear, and a few other things just to see what's going on. And the good thing about this is it will share your OBJ files between projects. So project A uses one OBJ and project B uses the same one. You only need to compile it once. And it works off the contents of the files, not just the dates. So if you copy a file from one place to another, it'll still be able to find it in the cache. And if you change it and change it back, it'll still be able to find the old file in the cache. Currently, you need to opt in to using the cache with your own files. Like if you've got a library with your own build.xml file, you actually have to explicitly set that you want to use the cache because you have to really get your dependencies correct. If you don't have your dependencies correct, and if you change a header file, the CPP build system doesn't know you've changed anything and won't recompile it. So currently that's opt-in, but I've put this into quite a few projects. It's pretty straightforward. Another thing I've got here is I can tag a compiler flag to be directed at an individual file. If you recall, I had the GC moving defined earlier. There's only one file in the whole code base that needs to know, well, no, GC moving is different. Everything in Hx needs to know that. Actually, well, there are other flags that only the GC needs to know about. And previously, if you added one of these flags to the command line, it didn't know which files needed, which ones didn't. It just recompiled everything. And now it will just recompile a single file if you change one of these compiler options that have been tagged at individual files or groups of files. And I've got a little demo at the end. So what else is new? stdlib I've added, so these are in the CPP package in the standard compiler. You get direct access into malloc and free if you want to do your own little memory stuff. There's some native GC stuff in there where you can create your own object with room at the end, like I've done with the anonymous objects and the enum objects, and then you can stick your own data in there, and then you don't have to worry about managing the lifetime of that object because it'll correspond to the lifetime of your larger object. I've added CPP finalizable as an easy way for doing a Hx finalizer. It's more efficient because you can't undo it, whereas before I needed to keep track of which finalizers could be removed. Here, once you add it, it's on. I don't keep track of how to remove it, so I can use more efficient structures underneath. The CPP also generates non-virtual functions where possible, so if you have a class that has a function in it, if that function is not overridden by any other class, it doesn't need to be a virtual function, and this lets the compiler, the real CPP compiler, make optimizations or inline it if it can. It's just sort of helping out the CPP compiler there. And the Hxcpp project has been contributed by Jeff Ward, and this is great for tracking down GC leaks and other issues with those Hxcpp allocations in general and profiling them. You can get a reasonable improvement just by seeing what's hot in the allocation path. Native gen is something else I've tried to sort of import from the Java way. If you tag up an interface with native gen, it will use virtual inheritance in C++, virtual multiple inheritance to implement the interface, and this means that the interface is not really a Hx object, and you can't query stuff on it dynamically, but you can pass it to external code that can then use this interface. And if you construct a series of interfaces and classes with static functions that only use native gen classes themselves in their function and variable definitions, you can create a bunch of external includes that you can give to someone else that are free from the hxcpp.h include. So it you're no longer bound to any implementation changes in the Hxcpp. So this is just a way of being able to use Hx to generate an external library with some reasonably decoupled header files. So just going over what I said last year, that I'd remove dynamic where possible, and I think the fake and non-types and fixed pretty much does that, and same with the enums. They no longer have the dynamic underneath them. I said I'd investigate some GC alternatives, and I have done that. There is quite some improvements there. Obviously, there's some more we can do. And CPU JIT didn't happen, and unless something changes, that it may or may not happen in the future. So I still want to have a look at some kind of generational or concurrent garbage collection, mainly to get down the pause time of the garbage collector if you want to use it inside a game. You don't want it stalling out for 10 or 15 milliseconds and dropping a frame. So if I can get that down to more like 1 or 2, that would be nice. I like to refactor the CPU code inside the OCaml compiler, which was something I didn't really get to because sort of ran out of time. And that should tidy things up again. And yeah, the CPJIT, until, I guess, unless someone really wants it, it might not happen. So just have a quick look at some of the demo for the compiler cache. So I'll make a quick little program here. Yeah, maybe I can. Jesus. There we go. I should have just copied this one. Alright, any mistakes? Take one out. So, enemy. So running NME on this, using this toolkit, which is using the native libraries that are now shared by... It was very fast because it was all cached. Let me uncache that for you. Cache. So here it's compiling the NME hex files as it goes. Now it's compiling the Hxcpp runtime files, string, debug, thread, class, dynamic. Now it's compiling zlib. Now it's compiling the NME actual CPP files that are part of the project, compiling them straight in. Now it's compiling the NME dependencies, which is FreeType, SDL mixer, mod plug, Vorbis, JPEG, ping, zlib, curl. Funny, this is faster. All right, so there we go. And circle. So that's 60 seconds to compile basically everything from scratch. Now if we go to a completely different project, of course it doesn't. Squat. Yeah, can't spell. I'll change this instead of that. So it compiles boot, which refers to the name, application main, which again refers to the name, but it's reused every other file in that compile tree. So compile time down to 4 seconds. So that's, I guess, the cache in action. It's put all the object files off in the cache directory, which is actually quite nice for, you know, source code cleanliness. Doesn't have to dump them all in your local area, so you can just blow them all away and start again anytime you like. You know, if you run any of the more complex programs, it will share what it can and what it can't. There's still some issues like with dead code elimination, that if one of the files has some functions not used in it, it gets smaller, you can't reuse that file. But you know, we can build up all the different combinations of the one file, because they're all, so it will keep them all in the cache. So you might be able to use some of them, not reuse some of them between projects. Different ones will reuse different subsets. So here it's compiling kind of all the Flixel stuff, but it will reuse all the NME stuff. It's doing regex. It hadn't done regex before, so it's doing it there. Doesn't take too long to compile. There we go. So yeah, so that's actually probably my demonstration talk for today. So if there's any questions, I'll take some questions. Yeah.
Thank you. The main question, when will it be released?
So the CPP code is already there. That's in the 3349. You can actually use the compiler cache today. But because, like for instance, the files that brought in this regex library here is in the 3.3 Hx distribution code. So it won't do much good until that's out. The RC's out on the website, so you can give it a go today. And obviously we're heading for a release of 3.3. I don't want to preempt anything here. Let's just say soon. So soon. Yeah, and that's so that's the time frame, I guess. Yeah.
Hey, so I was wondering, in the example you showed that promoted the dynamic array to an int array or to a float array or something.
Yes, yes.
Sort. Yeah, I was just wondering what happens if then at the end of that code I write a push string foo.
At the point of the cast, it's locked it in. So if you explicitly convert a dynamic array to something else, this array becomes locked as a float. If you push a string, it'll convert the string to a float, 0, and push a 0 on the end. So it becomes strongly typed at the point that you assign it to a strongly typed array.
Okay, so the code will kind of compile and the underlying structure at runtime will remain and then just coerce the value
yeah, so
as well as it can.
Yeah, as best it can. Yeah.
Okay.
Yeah.
All right.
Anyone else? Okay, thank you.